this video, we are going to solve an undetermined problem, and it is asking us to find the reactions at point B and point A using superposition. So, superposition tells us that if we have a beam like this, we can remove each force and find the deflections in the particular location and sum the deflections from all the forces. So this problem is undetermined and we have one redundant reaction, which is B. So in order to solve this problem, we have to break this beam into multiple beams. So for example, we can first remove all the forces and the redundant reaction, which is B, and replace this one with a force. So we are left with a fixed reaction, a beam, and a force at point B. And the length of this will be L. And next we are going to remove both B and one of the forces. So this will be like this. We have a force only at C and can remove all the other forces except the one in D. And now if we solve each of these problems, we find the deflection of this beam, and in order to find the reactions in B and A, we need one more equation, since this is not a determined problem, because in a two-dimensional space we have only three equations, which is sum of F in the x direction equal to 0, sum of F in the y direction is equal to 0, and sum of the momentum is equal to 0. So here we have four reactions, and in order to solve this problem we need another equation, which is this: the deflection at point B is equal to 0. And that means if we find the deflection here in this beam, and in this beam, and in this beam, and we add them together, they have to be 0. So we can find R of B. In order to find the deflection at point B, first we have to find the reactions, and then we can find the deflection. So in order to find the reactions at point A, we draw the free body diagram of this beam. Here we have R of A and A momentum, M of A, and we have no axial force because there's no load in the axial direction. So we can write the momentum equation around point A, which will be like this. Sum of momentum around point A has to be 0, so M of A will be equal to minus R of B times L, and we can write, and from the summation of forces we see that R of A equal to minus R of B, and from here we can find the momentum in this beam. So in order to find the momentum in every section of this beam, we have to cut through that section. If I want the momentum in this section, I have to cut it in here, which is X. This length here is, we call it X, so X is between 0 and L. And here we have a shear force and a momentum, and we have the reactions here as well. We can write M is equal to minus M of A, because both M and M of A are counterclockwise, so m of a goes on the other side of the equal sign and it receives a minus sign. And we can add r of a times x. So this will be equal to r of b times L minus x. And in order to find deflection, we put this back in this differential equation. So in order to find the deflection, we have to integrate this equation 2 times. At the first time, we see that derivative of y relative to x is equal to r of b times Lx minus x to power 2 divided by 2 plus c1, which is our integration constant. And if we integrate once more, we can see that y is equal to r of b times Lx to power 2 divided by 2 minus x to power 3 divided by 6 plus c1x plus c2. And in our problem, we had two boundary conditions, and since here we had a fixed connection, so the deflection, which is the derivative of y relative to x at x equals 0, is 0, and our deflection in here is 0 as well. So from these boundary conditions, we see that C1 and C2 are both equal to 0. So our deflection equation will be like this. R of B times L x to power 2 divided by 2 minus x to power 3 divided by 6. And since we are interested in the deflection in section B, we put L instead of x in here, and we see that y will be equal to R of B times L to power 3 divided by 2 minus L to power 3 divided by 6. And this is equal to R of B times L3 divided by 3. And we have to divide all of these by an EI. So this is the deflection equation for our first beam.